tomorrow?
Yeah. So it's I mean it's a great opportunity. It's secret, yeah. That's why you invite Sibertian, and he said I can't. So if you ever want to invite Sibertian, you have to do that at least 20 years in advance. It's not because it's very busy. It's the Dutch mentality. Their agenda.
No, but very happy that you. Very nice. So you were also at the Bienal this year in July in Granada, right?
No.
No? I thought you were in Granada. So maybe we can ask
Well, I'm very happy.
I don't know, maybe. Juanjo, ¿estamos? So the two are already so the population has the
the other ones actually probably were more math than mine is it's much like the course credit, especially if you're already gone through the MD part. I mean, the math is the same.
Yeah, so this is the microphone. Okay, so let's start. So good morning and welcome to the fourth day of the school. We are very happy that Manuel Melo made it to come here all the way from Lisbon. Manuel, you have the fittest student, the fittest participant from the school, so the others just leave it up. So it will be easier for you. So Manuel got his PhD in 2010 at the Physical and Biochemistry group at the University of Lisbon. Then I think he made a very long postdoc at the Molecular Dynamics group of the University of Groningen. He was working in the Marine lab, where he became involved in the development and also the application of Martini. At the moment, he is the head of the multi-scale molding lab at the Instituto de Tecnología Química y Biológica, which belongs to the University of Lisbon. And his research interests are focused in elucidating at molecular level the details of lipid-protein and protein-protein interactions. For this, he uses coarse-grained atomistic and hybrid molecular dynamic simulations. And well, please, the floor is yours.
Thank you, Inés. I don't know if you prefer I stand here or here. What's the? This is too tall. All right. So we're going to be talking about coarse-grained MD. Just a note. I'm from the Nova University of Lisbon. It's not the same as the University of Lisbon. It's perfectly fine, but if my science communication unit hears me not say this, they will kill me. So I have to say. Okay. With that out of the way, we're going to talk about coarse-grained MD, and this was built very neatly onto what you already learned from yesterday from Pedro Sanchez. Okay, so you already had a very strong primer on MD, and this is a particular case of MD, and basically we're going to turn stuff like this into this. Okay, so we're talking about simplifying. So just a very brief recap of what you talked about yesterday, but honestly, you already went in way more depth. So when you want to do a molecular MD model, you have to have several ingredients. You have to have your degrees of freedom. So these are represented by the atoms and the positions in space they can occupy. Then there's boundary conditions. Talk about PVC. There's other restraints or constraints like temperature that you have to keep, pressure and such, right? And this will define what can be sampled, right? What is possible to observe with your simulation. Then when you actually want to compute and progress this over time, you have to determine forces between particles. And for that, you need to define potentials between particles. You have the non-bonded potentials, you have bonded potentials. So non-bonded potentials are mostly intermolecular, or they can be intermolecular but at longer range. Bonded potentials, they typically represent particles that are connected by want. Usually that's how it goes. And with this, you can find your Hamiltonian, you can extract you can know the forces, and from the forces you can know the acceleration, if you know the mass and such. And because you know all that, then you can just move time a little bit, and essentially you just integrate the Newton's equations of motion. So this is high school physics. Super simple, and even the shape of these potentials, they are very simple. Not because we couldn't make them complex. It's just that the simpler they are, usually the easier they are to compute. So we are talking about very simple physics. And of course, you're on even at atomistic level, you know this already is an approximation. I'm going to come back to that. All right. So what kind of approximations are we talking about? So type of model that we use pretty much depends on what you want to study, right? If you're studying processes that involve molecules up to nanometers in size, or time processes up to nanoseconds, you probably can get away with using full quantum mechanical models. Okay, many of you probably already use them, maybe even more than I do, right? But from the moment you go above the nanometer scale, or above the even nanosecond scale, then you start having to go to atomistic MD, right? And okay, I think this is, you don't need this explanation, but essentially, if you go quantum, you are explicitly modeling electrons, electron distributions, electron clouds, and such, and the correlations between them. But then when you go to atomistic, not so much. You're collapsing electron existence into single points, and we assume it's the same point as the nucleus. It's very convenient. Then you just have to worry about one infinitesimally small particle instead of a distribution wave of several electrons. So this is much easier. And for all the simplifications, atomistic simulations they're pretty good at representing stuff. You can get a lot of realistic movements of both solvents and solids, such as proteins. There's a lot more things. You can do protein folding, ligand binding, right? So a lot of things. And you already talked about this, so you know what atomistic MD is about, right? If you need to go bigger, okay, this is where coarse grain comes into the picture. Of course, the question here is, I mean, I assume everyone here understands why we have this scale, right? If I could, I would do all my work at quantum resolution. Right? I just can't because the computers are not fast enough. And it might sound ridiculous to say, oh, yeah, I wish I could do my 100 by 100 nanometer membrane at quantum level, but hey, I don't know, like the cell phones are so powerful now, maybe in 10 years, this is going to be much more feasible than it is now, right? And I'm not going to talk about this so much, but there's also so many other kinds of approximations that you can go above the coarse grain. Okay, so there's many coarse grains. So when you talk about coarse grain, this is not so well defined as when you talk about, say, atomistic MD. Atomistic MD, there's pretty much all the models do more or less the same approximations. There's some differences, but in coarse grain, you can have it can be different from type of model to type of model. I like to use this term, and this is by no means a hard term, but I like this term. It's some models that sacrifice atomistic detail, but you can still tell molecules apart, right? And still, there are some coarse grain models that kind of clump molecules together, right? This would be like supramolecular coarse graining. The kind of models I work with and that I'm going to talk about, you still kind of separate the molecules you're working with. But just an example, so we have octane here, and well, one possible coarse grain would be the one that we had in the first slide. But this could be also a valid model. Instead of two particles, it could just have a single particle model for octane. And honestly, whether it's suitable or not, it pretty much depends on your application. There's probably going to be applications where a point representation of octane is going to be perfectly fine. And others, if you want to talk about heat capacities and such, that probably it's not going to be fine. So it really depends on what you want to do. You can even do something like this. You can even have non-isotropic potentials. Honestly, I've seen those things, but they tend to be so complex to compute that I just use two particles just for simplicity. But it is possible. So all these are possible. So I think there's much more variety in the types of models that you can have once you go to the coarse grain simplifications. Okay, so why are they faster? Okay, why are they faster? Why is coarse grain faster? Like less particles. Okay. So yeah, I usually give this this lecture to a class that doesn't have so many chemists, and so it's not always the people are quick to come up with that justification. Because exactly that. There's less particles. There's going to be other two very important details, or a couple of more important details where it's also faster, of course, right? But we're going to come to that a bit later. So, okay, so now we decided to go coarse grain. We're going to start representing parts of our molecules as single particles instead of being multi-atom moieties. Now they are single particles. But now that leaves us with a problem. So if I want to create my model, how do I decide how these particles, we call them beads to distinguish from atoms, how these beads interact? The parameterization strategies, they are a bit different than what you usually have at the atomistic level. So at atomistic level, you often have a lot of physical data, like atomic radii and stuff like that, that will give you a good experimental hint of how two atoms, how close they should come together. You can do even quantum calculations to see, okay, what is the average load on forces between these two kinds of atoms and such. So in coarse grain, you're not talking about atoms, you're talking about the bunches of atoms. So it can be a bit tricky to define and to know exactly what is the procedure you should take. And actually, there is no single procedure. So there's different types of models, and I'm going to show three that take different roads to parameterizing interactions, right? Also, as an example, using the bonded potentials in an atomistic molecule, you can very cleanly take the force constant of a molecular bond. You can take it from infrared spectroscopy, right? You can directly take the frequency and the force that the bond should have. But in coarse grain, I mean, those two particles in that octane that I showed, that bond doesn't exist. I mean, there's no infrared spectroscopy that's going to give you the frequency of that bond because there's no such thing as that bond. We are already a bit one level higher in the approximation, so this is a bit further off from experiment. Anyway, so I'm going to start by the models that I don't like so much, so I can spend more in the models that I do like. So this is what I call structure-based parameterization. And one of the ways to find how our coarse grain particles should interact is to do something called Boltzmann inversion. Essentially, and I'm now talking about the interparticle potentials. This also works for the intermolecular, but let's say intermolecular, now we're doing the intermolecular non-bond potentials. We're intuitively going to find a potential that reproduces a target RDF. If I say RDF, who knows what an RDF is? Who doesn't know what an RDF is? Okay, so an RDF is, well, an RDF is when you have a solvent system, a bulk system. It doesn't have to be a bulk system, but imagine a bulk system of a solvent is the distribution of all-to-all particle distances with some normalizations. But what that brings out is that you're going to have, so at very short values, the distribution of distances there is going to be zero. Those particles are not going to be together because there will be reflection. Okay, so that distribution is going to be flat. But after a little bit, you start having a peak corresponds to the first neighbors. But then also, usually you have a peak, it comes back down because you have a shell of first neighbors. Right? Then usually have a second peak. A little bit, if it's a liquid, it will be a bit softer, corresponds to second neighbors and so on. So this is a very easy way to kind of visualize the structure of a liquid. It could also be a crystal, because these things are very sharp. But it's a 1D function that represents a lot of information about the system. And if you can get particle-particle potential that reproduces that in coarse grain, that's already a very good very good approximation. So how do we go about that? So we use an atomistic simulation as a basis for our coarse grain parameterization, and I'm showing that by these gray molecules here. So the gray, these are hexadecanes. So these gray hexadecanes are here, and what I do is I take the frames of my atomistic simulation, and I place my coarse grain particles where they would correspond. This is called mapping. So in this hexadecane, I'm saying, oh, this hexadecane is going to have 4 particles, and each of them is going to be, well, at these positions along the chain. Right. So I have a sort of a coarse grain trajectory, only it's not really coarse grain. It was obtained atomistically. I just mapped it to coarse grain. All right. And what I do is for every frame, I do this RDF of the mapped coarse grain centers. So I take each coarse grain center, and I see all the distance between this center and the other centers, and then the same thing for that one, and for that one, for every center versus every center, right? And then I do a distribution of this. And then I see whether, when I do my own, so this is how a RDF typically looks. At short distances, there is repulsion, so you're never going to find something at 0. Then you have first neighbors, second neighbors, etc. What then I want to do is find a function that represents the particle-particle interaction, that when I simulate my coarse grain system without any knowledge of atomistics, without any atomistic force, the behavior of the coarse grain system results also in an RDF like this. So essentially, I'm training or iteratively fine-tuning my coarse grain system that it has bulk properties corresponding to what a mapped atomistic system would have. All right. So this is the idea behind this Boltzmann inversion. There's a very similar approach, or a related approach. It's not so much in this bulk structure. It's about specific interparticle forces. So this is called force matching, and it's, again, let's say the same example. We have our atomistic simulation. We have the particles, the coarse grain particles that correspond to certain atoms. And what we're going to do, we're going to find the average force that the atoms corresponding to this bead feel by interacting with other beads. So, okay, the atoms from these beads interact with those from that bead, and then I compute those from that bead with this. So what this will give me is a measure of force that this particle feels as a function of distance to other particles. Okay? And if I do it averaged by the coarse grain bead, I'll be able to have a sort of a interparticle potential function that should represent the mean force between these, that these particles should feel in the coarse grain system, right? So, and then the result is the same. If I can match that in coarse grain, in principle, I should have a quite reliable fine structure, right? Because this is something I'm parameterizing for. All right. So this structure-based parameterization models, this is what I talked about. They have the advantages that they're very accurate at a specific state point, right? So you find, okay, at this density, at this temperature, usually they're very accurate in the structure of the system that you get out, because it's exactly what you're parameterizing for. The parameterization process is also very well defined. It's not like, oh, do I do this or do I do that? No, it's make a script. This is for you, right? And of course, because it's in the name, the structural properties are well reproduced. Now, what's not so good about them? So they are of course biased by the underlying models. So you're matching this to an atomistic behavior, right? So if your atomistic model itself is already an approximation, if it's not a good one, so you're just piling up error. There's limited transferability, and honestly, for me, this is the biggest deal breaker, which is every time you want to add anything new to this system, you have to repeat the process. Oh, now I want to say hexadecane mixed with water or whatever. Okay, but there is no parameterized interaction between hexadecane and water in these circumstances. So you need to redo the entire process now with water in the system. Oh, now I want to have a protein there. Okay, repeat. So every time you want to do something new, you have to go through the entire parameterization process again. I think that is, for me, that's the worst. Then something that also is quite interesting is that even though usually the fine structure of the solvent tends to be correct, the thermodynamic properties like vaporization enthalpies and surface tensions and such, they tend to be off because these are a bit more emergent behavior, emergent properties of a phase, and not so much so dependent. Well, they depend very much on the fine structure, but they depend on more than that. So then those tend to be off. And finally, might be or not important. The potentials that you get out of here, they are numerically defined. They're not. It's not an analytical function. And for some software, that might not be very easy to handle. So it depends on the software you use, whether this is a problem or not. All right. Next model. Heuristic parameterization. This is the kind of model that I like more. It's the model I work with. I don't know if you've heard about the Martini model. So this is the model I've been working with already for many years. So yeah, I'm biased, already saying. But so here the interactions are not targeted to reproduce specifically fine structure in all its aspects, but there is some structural characters of parameterization, but a lot is also the emphasis is also put on whether the larger scale behavior is correct, right? So let's see. So let's do with some examples because it's much easier. And these examples, so this talk comes at the right time because just last year Martini 3 came out. So there's changing between two types of Martini, and I'm going to show you a little bit of both. So I'll kind of note here like the differences. But okay, so when you make a new molecule, what do you need? So we need to define a mapping. This is just like in the examples before, where you decide, okay, I have an octane, I want to put two particles, and these particles are going to be placed at the center of mass of some atom, something like this. So you have to decide where the beads are going to be placed relative to the molecule. So this is called the mapping. What else do you need? In Martini, this tends to be around 4 heavy atoms to 1 bead, heavy in the sense of non-hydrogen, right? So we try to aim for that ratio. In Martini 2, this was more important that you stuck to it. In Martini 3, you have more freedom. I'm going to talk about that later. And these are some examples. So this is a lipid, for instance. In the lipid tails, you have one particle, more or less 1 every 4 atoms, 2 particles for the glycerols, and then the head group. Cellulose could be mapped like this. It's you can see that there's some atom sharing. These particles here, they have this particle, the ring particles. They were sharing some atoms with the edges. And proteins, for instance, you can see similar things. There is some details. For instance, here in the phenylalanine, you have a phenyl ring, and this is nowhere near 4 to 1 because if you have six carbons and you want to make a ring out of 6 carbons, you need at least 3 particles. So at best, you can do 2 to 1. That's more or less what's done here. This we found out later did introduce some artifacts. The fact that we are using potentials that were made for 4 to 1 mapping, and then we're using smaller mapping, and hence Martini 3 exists to fix that. I'm going to talk a bit about that. So this mapping that you choose is not unique. You could think, okay, I don't know, some of these particles, they could be, instead of representing this part here, I could think that, oh, it's represents more this side, and I put another particle there. So how you arrange the particles, the beads, over your atomistic model, it's not a one-sided solution. And there's a bit of art to it because there's many factors that you have to juggle at the same time. So you have to use some chemical intuition that you have some particles that will represent, for instance, in this case, these models are very much used for apolar discrimination, like in the case of lipids. So it's good to have particles representing apolar stuff, particles representing polar stuff. If, for instance, I had a particle that was half in the ester, half in the aliphatic carbons, it would be kind of middle character, and maybe it would not behave as well. So a little bit of chemical intuition, whether this makes sense or not. Inspiration from other existing molecules. This of course makes sense. It also makes it for consistency, which is important. Like if you have several molecules and they are pretty much the same, with some difference, it doesn't make so much sense that they are represented by different coarse-grained models. I can think, for instance, like hormone, cholesterol, stuff like that. You have the same backbone and then some difference in some tails. So the constant part should be constant. This is no hard rule. So you can always change whatever you want, but this is strong advice. And also something like trying to respect symmetry. And there's an example about that. So again, be consistent. So because it's with existing molecules, but even inside the same molecule, right? An example about the symmetry. So if, for instance, if you wanted to parameterize toluene, how would you place the particle? I could say, okay, I want this, and these three atoms to be one particle, and then these two and these two, something like this. But then this layout actually would not keep the symmetry, so the molecule is symmetric, and this would break that symmetry. So maybe a better idea is actually to do something where you say, okay, there's this one that has these 4 atoms, but actually because this would be too many atoms for this particle, we share, and this one has 1, 2, 3. So this atom here is shared between the 2, and this one is also shared between the 2, right? And then you have a triangle. This is just an example of the considerations that might come at play when you decide how to map. Okay. So when you now go to this modern Martini 3, what changes? So one thing that became very important is that now we can explicitly say we want to map 4 to 1, but also 3 to 1 or 2 to 1. There are different types of particles that you want to map, something like benzene rings, where you say, okay, this particle corresponds to 2 carbons, and that the interaction between that particle and the rest of the world is going to represent that, and they're going to be smaller. So that is good. Also, another thing that became very obvious is that it's important to try and represent the occupancy volume of a given molecule. And an example is this. This is work we did recently about parameterizing phosphoinositides. So you have inositol with some phosphates, but what's important here, and I'm showing, is so we have our bead placement. So there's an atomistic model there, and there's our bead placement, these spheres. And in this blue shape, in this blue mesh, is the conolid surface, the solvent accessible surface area of the atomistic model. So this is essentially the surface of closest approach of a solvent to this molecule. Okay? And now we're trying to reproduce that as close as possible with our coarse-grained model. Of course, it will never be exactly the same. You can see that the atomistic model is going to have a lot of detail because of the hydrogen and such, and the potentials that we're talking about, of course, are spherical. So there's no way I can get a sphere to have bumps, sphere, right? So this is why the coarse-grained one, which is this orange pink mesh, is coarser, but overall tries to reproduce this. Okay, and we did, I think, an acceptable job here, and this turns out to be rather important in preserving representativity in molecular interactions. The consequences, if the coarse grain is actually much smaller than the atomistic, you end up exacerbating some types of interactions, namely heterophilicity, and it's a bit annoying. And from Martini 3 onwards, also you can have partial charges. So typically, Martini molecules are neutral, or they have the formal +1 charge. But some cases now, especially resonance systems where you have distributed and the resonant charges, it might make sense to have some partial charges there. It's not very well tested, so use it to your own risk. All right. So we're deciding where to place the particle. This was the setup. Now we know I want to have the particles there. Now I have to decide 2 things. How these particles are going to interact inside the molecule, the bonded potentials, and outside the molecule, the non-bonded potentials. So you already know this from yesterday. I don't say much about it, what's the bonded and non-bonded. But essentially, the target here is going to be to recreate target or experimental behavior as much as possible, or to have some high fidelity behavior that we want to reproduce. Where does it come from? So if you're lucky, you're going to have experimental data. And I'm going to give here two examples. For the bonded part, so for the intermolecular distributions, you want to have your molecule experience the same range of configurations that the real molecule does. That's very nice to say. But what does this mean? Okay, I have two particles. In this example here, this is an example from when the proteins were parameterized. So I have this molecule, and at some point I have to decide, okay, I have this particle represented in this backbone of this residue, another one, and there's a distance between them. And I need to know that distance. I'm going to put a harmonic potential to keep those things connected. So what's the equilibrium distance? What's the force constant? And there's a huge database to help me. There's the PDB, the protein data bank. So I can just go to the protein data bank, take out a couple thousand structures or million structures, whatever. I can coarse grain them. So I place the coarse grain beads where I want them to be with respect to the backbones, phrases, and then I measure the distance between the consecutive backbones. It's quite simple. And what you get is something like this. This is a distribution of distances between particles. There's three because they correspond to either random coil or beta sheet or alpha helix. So it depends on the secondary structure. It actually makes sense. But you can see that the distance is going to be somewhere between 0.3, 0.36 nanometers. And then it's up to whoever parameterizes to choose an adequate force constant that when this coarse grain protein is floating in the system, these distances end up more or less in this range, right? And you can even go further, and this is what Martini did. If when you create your protein system, you say, oh, this is going to be an alpha helix. Oh, then you already place your beads a bit apart. You don't need to use a single potential for all these particle-particle distances. If it's an alpha helix, oh, you're a bit further. If you're a random coil, you're a bit narrower. All right. So this is one example how you can use experimental data directly to inform your coarse grain parameterization. For non-bonded, so the non-bonded in Martini in this case, it pretty much depends on choosing what you call the particle type. Usually you have a large library of particle types to choose from, and each of them will interact with the other particles with a given strength. We're talking about Lagrange potentials. So those Lagrange will have different sigmas and epsilons. And so how do you choose the best particle type? And one way to help guide that choice is to look at partition data. And the choice of this kind of data might seem a bit random, but this kind of models, the Martini models, they are very much used for biomolecular simulation. And a lot of the forces, a lot of the interactions involved in the simulations are polar-apolar discriminations. Whenever you have membranes, protein-lipid interactions, water hydrophobic effect, it's a lot mediated by that. There's a lot of electrostatics as well, but a lot is mediated by polar-apolar discrimination. And when you go and look at the wealth of literature that there is on putting stuff in octanol and water and seeing where it goes, that's a very good hint if your molecule is behaving correctly. This is more useful for smaller molecules, but it's a very cool way of matching with experiment. And I'm going to actually show how it can be done in simulation. You can simulate this kind of experiments. Now, let's say I'm doing a model that no one ever did a structure of. I don't have any experimental data, neither here nor here. So what do I do? So you can always get this kind of data, not from the PDB or any structural experimental bank, but from finer simulations. You can always do simulations with an atomistic model. And if you trust that model enough, well, it's better than nothing, right? And then you can use it just like this, right? And I'm also going to give a bit more specific example. And just like we can simulate the delta G of optimal water partition for a coarse grain molecule, we can also do it for an atomistic model. So we can essentially do the same thing here, but simulate it on finer model. And I mean, it's not as good as a real thing, but better than nothing. So how do we get the right potentials when you're talking about the bonded part, the bonded potential? So usually, what do we use? So if we're talking about bonds, really harmonic bond. Most of the times, it's what we use. I don't remember the last time I used something that was not a harmonic bond. Makes sense. Okay, simple, it's stable. Now the angles get a bit trickier. The angles, very often in atomistic models, you're going to find this angle potential essentially is proportional to this difference between the target value and the angle value, the square of that. But this, here represented in red, this one is not numerically stable close to 180 degrees. You can see at some point, of course, you're going to have to make a derivative, get a derivative of this because of to get the force acting on the atoms. And you can see that the derivative is not defined at 180 degrees. On the other hand, this other potential that is proportional to the square of the difference of the cosine between the angle and the target value has this behavior that has the minimum and then very softly goes to 180, and the derivative is always 0 at 180. So this one is more numerically stable. This is one interesting difference between coarse grain and atomistic, because atomistic models, when you're working with angles, they are usually very, very stiff. I mean, you're working with water, that angle is 109 point something, and even if you allow that to fluctuate in atomistic simulations, it's going to fluctuate by a couple of degrees. In coarse grain, this might not be the case. In coarse grain, the angles, they are not representing atom movements, but moiety movements. And those things have much larger range of movement, right? So now we can be talking about something that can be collapsed and then suddenly goes all the way and it's collinear. So, and this can be a bit problematic, not problematic, but we're facing some challenges that people that did atomistic simulations never had to worry about. So that's why we use this kind of angle. All right, more. We can have torsions. This is pretty much like other torsions in other models. They can be of two types. You can have the periodic torsions, like stuff really goes around, or especially if you want to keep stuff planar, you can have a non-periodic potential there. So this is how they would look. So this goes from -pi to pi, and the periodic would be periodic, and the non-periodic will be non-periodic, and typically you get into trouble if you have one of these red ones and you try to go too far from the equilibrium, but the point is that you don't, so this is usually fine. But these torsions do introduce a big pain, which is these will be unstable, numerically unstable, if the constructing atoms become collinear. So when you're calculating torsions, what you're calculating actually is the angle between two planes in space. And if you have the torsion between atoms 1, 2, 3, 4, you get the plane of 1, 2, 3, the plane of 2, 3, 4, and you get the angle between those two things. Very easy. But now suppose that 1, 2, 3 are collinear. If 1, 2, 3 are collinear, there's no plane. It's not defined. So this is the intuitive explanation of why these things become unstable. If you go to the math, at some point you're going to do some derivatives. You're going to end up with a term in 1 over sine. So whenever this goes to close to 0 or 180 in this case, you're going to have a singularity. And even the singularities, you could deal with it, but this is one of those singularities that goes to plus or minus infinity when you're very close to it. So when these angles here stretch over to 175, 76 degrees, boom, your system explodes. This is very annoying, and it's kind of still a bit of work in progress. But the way to deal with it is on the angles. If I'm suspecting that this angle might become too straight and destroy my torsion, but I use a specific kind of angle potential. It's a specific one that goes to infinity at 180, so it does not really let it become fully extended. It's sort of the stopgap solution. It's not ideal, but it can still get quite straight. It's not straight enough to explode our system, and most of the times we're happy about that. There are other solutions, and a couple of years ago I reviewed a paper that had a much cleaner analytical solution. So I hope that gets implemented soon. All right. So, okay, I decided, let's say I'm talking about the bond. So what's the typical approach? So we get our target distribution, again, either from the PDB or from an atomistic simulation. And then we look at it, the equilibrium point is more or less around 3 angstrom, and the force should be, I don't know, 2,000 kilojoule per mole per nanometer square. And then you simulate it and see what you get. And then you compare, and then you repeat. And I'm going to show here. So this is an example. I was working with this molecule, bacterial analog of cholesterol. Doesn't really matter. And I was parameterizing the distance between these two particles. And in black is how they behave in an atomistic system. And in red was my first guess. I looked at this. And I said, I think the equilibrium is at 0.415, and the force constant should be this one. And I simulated. And of course, when I get this distribution, it's too broad and a little to the left. So next attempt, well, I kept the same equilibrium point, but increase the force. Still a bit too broad, a little bit to the left. So next try, stiffer and a little bit to the right now. And I think at this point I was happy with it. So this is a typical way of going about it. Of course, you can maybe some of you already think, oh, I can teach a computer to do that, and that's true. There's many approaches now that actually do this automated. If it's a small molecule with not so many parameters, you're probably better off doing it by hand and having a good feel for the things that the interactions in your molecule. If you're doing a couple, already 10 molecules is probably hard enough that you probably want to automate the procedure. More details, more tips and tricks. Sometimes you're going to have very highly localized distributions. For instance, if you are trying to parameterize the distances in a resonance ring, something like this. These distances, if you do the atomistic simulation, or even if you just do quantum fluctuation analysis, how they really don't fluctuate much. You know, this is very stiff, right? So you're going to be looking at a distribution that oscillates between 2.1 and 2.1 and 2.3 angstrom, something like this. This can be a bit problematic if you want to reproduce with coarse grain. You're just seeing that if I want to have a very highly localized distribution, I have to increase the force. To have an almost infinitely localized distribution, I have to have almost infinite force. And high forces are usually bad news in molecular models because high forces lead to high frequencies, and I'm going to show an example why that's not good. But essentially, in that case, the use of constraints is very important. I don't know if you talked about this yesterday or not, but essentially, it's a way of telling the system that this distance here is constant. You really remove that degree of freedom from the system, and it's simulated at a constant distance, in this case, as a triangle. So this, you don't need to worry about trying to reproduce that kind of distribution by using force. You just simplify the system there. This is the diagram of how Bromax software that I typically use, that we're going to use in the practicals, how it deals with the constraints. You don't pay so much attention. More tips and tricks. If you have any experience dealing with atomistic models, you'll probably be used to seeing every possible angle and torsion parameterized. So if you have a molecule that looks like this, all of these angles, all of these torsions will have a potential on them. In coarse grain, in my experience, less is more. And why? It's because a lot of the torsion and angle behavior is already encoded in the particle-particle non-bond interaction themselves. And often the system does a good job with the non-bonded already, that you don't have to put a lot of bonded. And the thing is, the more free you leave your model, if it still reproduces reality correctly, the more freedom it will have to reproduce reality that you don't expect. Like, if you make these models because you want to study unknown stuff, but you make sure that they are good by trying to reproduce known stuff. But if you tie them very tightly to the known stuff, they will have a hard time doing the unknown stuff. So you should leave them as free as possible, that they still reproduce the known stuff, and have enough freedom to give you information about the unknown stuff. That's a bit the idea. In terms of parameterization, also, if you put too many potentials, it becomes a nightmare to actually get stuff right. Because at some point you want to move an angle, make it tighter. But there's another angle potential on some other particles that's affecting that indirectly, and tighten, and the particles don't get tighter, and it has to do with this cross interaction. So makes your life easier and is also better. There's also other advanced tips and tricks. So let's say this is a complex glycolipid head. So this is a multiple sugar head, and these were the particles that were being parameterized. So each of these groups here corresponds to a coarse grain bead. And what happened is, so this is in concept is like two triangles connected by this particle, connected by this bond, all right? And then one interesting thing is that the distance between these two particles has this distribution, the black one. Now, you see that this distribution atomistic goes below 0.40 something. And in the Martini 2 model, where this was parameterized, these particles, this type of particles, were actually they become repulsive already around here. So this left side of the tail could never be reproduced by your own coarse grain model, because those particles were already repelling one another. So, and that's one of the cases where you might look at this angle here, so this angle here, and you see that's too open because those two particles are repelling, but you don't notice they're repelling, so you just put a force to tighten the angle, but it doesn't work because you're just fighting against the Lennard-Jones repulsion of the two particles. So and then you realize, and what you do, you can just say, okay, the two of you just stop interacting. That is a solution. Or sometimes you can put a bond there. I mean, there's no chemical bond between them, but you can just put in a harmonic potential between them that holds them at the right distance. So these are all acceptable solutions, right? But it's good to bear in mind that these problems can happen. All right, now let's talk about the bead types. The bead types is what's going to give you the non-bonded interactions, and by extension reproduce those in ultimate case the octanol water partition, so the selectivity of the molecule for interaction with other molecules. And let's say again the same example. So this is the molecule we were working with. For the Martini models and for other models like this, you're going to have kind of a Bible of particle types. So we're looking at something here that looks like a branched alkane, and here a diol. And we can see okay, here we have branched alkane and diol, diol here. Okay, and there we go. This should be the types of particles. This is very direct, and just looking up in the telephone list, very easy. There's many aspects that you might want to consider getting it one direction or the other. There are many reasons. If you have reason to suspect that a part of your molecule has extra charge because of a charge donor or charge withdrawing group, then you can consider using other particles. But this is a very good starting point. All right. There is also for Martini 3 a lot of other considerations about now not only the type in terms of polarity. That was what you saw there before. It was kind of a scale of polarity. But in terms of size, so as I told you now, Martini 3 can have 3 specifically different sized particles, corresponding to 4:1, 3:1, or 2:1 mappings. But for instance, if you have a 4:1 mapping, but that is branched, you should use something that's a bit smaller, because if it's a branched moiety, it's going to take up less space, so you probably need a smaller particle. Or if it's 3 particles, but they are in a resonance system, they're going to have a flatter profile, so you can use what you call the tiny beads, the tiny particle. So there's a couple of considerations here. This is in the supplementary material of the Martini 3 paper, so this is something that you can have access to, all these tricks. So yeah, I'm not going to go much more in that direction. Cool thing, just for you to have an idea, how can you get this partition-free energy from simulations? I mentioned, okay, let's compare with experiment. You have the octal water partition. This has been done for over a century, and you want to compare to that source of data. And you could do the same thing in your simulation box. You can actually simulate water with a apolar solvent, in this case, octal water or something like this, and you just put your solid in there, and you just simulate. And then later you go and count how often it was in one phase versus the other phase. It works. The first Martini paper was done like that, but there's problems. So you really have to have significant counts in both phases. If you have something that's very hydrophilic and it's all the time here, I mean, you can't compute a ratio. It's going to be something over 0. So you can't really get an affinity. You say it has a high affinity, but you can't distinguish between, you can't get an energy value there. Then very annoyingly, a lot of molecules really just like to sit at the interface. They sit at the interface, one moiety to the polar side, another moiety to the apolar side, and then what? You can't count them. And then also, if you want to use atomistically, this is too expensive. This is already hard to do in a coarse grain. If you want to do atomistically, then much slower. So how do we do it? So this is what we want to have. We have our solid in water, and we're going to get delta G of partition into our solid in an apolar solvent. Here I use HD as hexadecane, but could be any apolar solvent. And we're actually going to get this through the other two edges of this triangle, where we just get the solvation energy of the solid into water and the solvent into hexadecane. So if I can get these two, I can get this one by difference. And essentially, we're talking about this. So I have the system with my solids in water and my solids in hexadecane, and I want to get the energy of this reaction. But you can't just simulate these two systems and try to compute the delta G. It doesn't work like that. The method that I like to use, essentially, intuitively, what it does, it asks the two systems how often each is in a state that is low energy in the other. Okay, and these two systems are too far apart to ever have meaningful counts in those categories. So what we do what's called now chemical transformation, where we start with our solids in water, and then our solids in water. But now the interactions is only 90%, 70%. And a bit weaker, in our solids in water, but with 0 interactions. So this system now, essentially, it's this one. Like our solid is alone because it's not interacting with the water. It's like we have our solid and the water box separate without interaction, which is practically this state here, right? We're taking the solid out of the water. The water still exists, it's just not in the picture. So, okay. The interesting part here is that now we can actually compute the successive small delta G's from here to here, from here to here, from here to here. We can get this. So overall, I can get this overall delta G and do the same thing here, and then get this. Now, you might ask, yeah, but this makes no sense. I'm studying a sugar in water, and there's no 0.7 interacting sugars. What is that? Delta G is a state function, so it doesn't matter because only the endpoints need to make sense, right? That's the cool thing. So whatever happens in the middle, we can do really whatever we want as long as we can compute the delta G from that. And that's actually pretty neat and matches experimental data very well. So that's pretty cool. So, and yeah, this is always more efficient than actually simulating separated phases. And you can use atomistic systems with this. So this, I've used this in the past. It's a pretty good source of data for comparing. All right, but so I've been giving a lot of examples of how you parameterize bonds, how you parameterize D-types. And very important thing is probably you'll want to tailor this approach to your application. So if you're doing molecules, and so in biomolecular applications, a very big focus is put on hydrophobic preferences, hence this comparison of the partitions. But we don't really need to just look at that. And for instance, when we did when the proteins were made, they were parameterized. It was very important, for instance, how these things would interact with the membrane. So the profiles of interaction with the membrane, energy profiles of interaction with the membrane as a function of depth into the membrane of the amino acid side chains were also computed and compared to atomistic data. In that way, we could know whether it made sense or not to have, if that amino acid behaved well, if you try to put it in the membrane. And other examples, for instance, when these sugar head groups were parameterized, because these things are important in aggregation. So the profiles of aggregation in atomistic simulation were compared to the same thing in coarse grain, just to have an idea whether the overall behavior would be correct. And in cases where they were not, there were some adjustments made so that this would match. So this is an example of actually tailoring your approach a bit to what you want to do with the model, right? So to round up this heuristic parameterization of the Martini model, what's good about it? It's quite broadly applicable and transferable. The transferable part here is that I can parameterize some molecule here according to this overall Martini philosophy and another separately. And the chance that if I bring them together, they will play along realistically is quite high. Okay, so I'm quite confident, or I like to be quite confident that the two molecules together will behave realistically. Whereas the examples I gave before, if you want to bring together molecules that you've never parameterized together, you can't do. You really have to redo the parameterization work. It's typically relatively easy to use, essentially because you have fewer potentials and they're simpler than the atomistic. That's great. And the thermodynamics are usually well kept because it's usually something that we aim to reproduce. It's also not a big surprise. What's also good about that, as with most coarse grain models, it's semi-quantitative. So often you're not going to be asking absolute values from a system, but rather the system A have a higher tendency to interact than system B, like this, tendencies and differences rather than absolute values. Of course, also with any coarse grain, you're going to lose chemical fine detail. This, of course, is important. If you want to do very fine modeling of chiral recognition, probably you're not going to use something that represents your moiety as a single sphere that has zero chirality, right? So this comes with the territory. There's ways of getting around some of the loss of detail, and the structural features sometimes are not super well kept. This is a bit by contrast with the models I explained earlier, because we are only trying to keep structure to a certain degree. The other part of the parameterization is to reproduce larger scale emergent behavior. Still, I do prefer this kind of models. Just an example, for instance, of these two last problems, proteins. So proteins have, if you want to do secondary structure of proteins and model that, you're going to depend on very specific hydrogen bonding networks. If you imagine an alpha helix, for each backbone particle, for each backbone of each residue, you're going to have carbonyl pointing to the amide of the residue one turn ahead. Okay, and each of these residues is going to be doing this back and forth. Now, I showed earlier that you could represent the backbone as a single particle. But if you have a single spherical isotropic particle, there is no carbonyl and amide pointing in opposite directions for this to happen. So it's already a bit hopeless to get secondary structure with a coarse grain like this. So what do we do? Well, actually, if we want to simulate, if you don't expect our protein to unfold, if you know its structure, and we do know the structure for many, many proteins, we can actually enforce that structure. You say, okay, you're going to be a helix, and we keep it like that. And there's several ways. One of them is to use something like elastic networks. I know you talked about that yesterday. Essentially, you just place a network of harmonic bonds that keeps the backbone particles at predefined distances that match the structure, right? And that will more or less preserve the structure of your protein, even though intrinsically it could never find it on its own. So this is one way to go around these problems. Now, another reason why we put up with these problems is, okay, we usually present 4 for one thing, so you get fewer particles, which gives you a speed up. And this is the other aspect that I wanted to mention. You're going to have a smoother interaction landscape. And why this happens is the distance distributions and between particles, either in the molecule or in between molecules, are going to be much softer because they would correspond to averages versus atomistic cases. And this means that the potentials that you're going to use are often way, way softer than atomistic ones. So if you have softer potentials, meaning weaker forces, you can use longer time steps. And all this together usually get up to 1,000 times speed up compared to atomistic. And this 1,000 here is why we put up with this, right? Because I'm not defending that it's good to have proteins that don't know how to fold, right? So this is just an example. If you're not yet seeing why softer potentials can lead to larger time steps. So let's say we have the distance between two particles, and they are in an oscillator, a harmonic oscillator, and you want to sample this, integrate this over several steps. So usually, okay, if the particles are here at this distance, they're going to be feeling a force in that direction, and something like this. You do several steps, it goes in the other side, feels the opposite force, comes back, goes back and forth. Now, if you repeat the same exercise, but use a very long time step that doesn't allow proper sampling of the harmonic curve, what you get is something like this. You have a force, it kind of overshoots, and at some point you start getting more energy than the system has, and it's not going to end well. But now, if you redo the same thing with a much softer potential, you can use huge time steps, and everything is fine, no one gets hurt. And so this, you can typically use 10 times, even more, 15 times larger time steps, of course, going in atomistic. So you just get 10 times speed up just because of this, right? So another big part is because of the fewer particles, but the big part is also because of this. And okay, so before we go into multiscale, which we combine different resolutions, I think it's time for a little break before everyone melts. Questions?
Imagine that I have a system, I start with coarse grain, and I am starting, for example, the open only in the whole thing. That doesn't happen in the all atom simulations and the time scale. How can I go back from the coarse grain to the all atoms if I want to study specifically?
Perfect. That is part 2. That's multiscale. That's what I'm talking about. More questions?
Well, about electrostatics.
Yeah.
Because if I want to reproduce the hydrophobicity, hydrophilicity, and so on, and I have like neutral beads interacting, the Lennard-Jones is efficient enough to describe those kinds of interactions, or you avoiding the electrostatic because you want to avoid those long-range interactions to cost less, and be more efficient, stuff like that.
So, in all honesty, systems where electrostatics plays less of a role are going to be easier to simulate. Everything is electrostatics, even London forces. Lennard-Jones is just a simplification of electrostatics, but it's perhaps better simplification than our Coulomb interactions that are long range. And worse, in Martini, they are very much localized in only the particles that have formal charges. So for instance, in the example I showed, only the phosphates and the colines would have +1 or -1 charge, and everything else would just be a chargeless desert. So yes, this can be a problem. One way, if you know that your system is being misrepresented because the charge is not interacting properly, one strategies that have been used is to use polarizable model. So the polarizable model will have explicit dummy charges that can respond to induced dipole, form induced dipole, and those will usually afford you better realism, especially where water is concerned, because even the water model, so the water in Martini is also one particle represents 4 little waters, but it's also charge neutral. But you can also have polarizable water models that do respond as a dielectric would, and then you can have explicit charge screening, and the system would overall be more realistic. Yeah, but also from experience, that starts to be important when you go to real strong charge interactions. Stuff still at the level of OH interactions, this kind of dipoles, this is probably still fine. Some kinds of amino acids, if you have very polar side chains, then it might make sense to have them polarizable. And it, of course, depends on your application. Yeah, but do be critical, right? It's not just saying, oh, I'm doing this, it has to be good. No, no, no. Sometimes you really have to, the model can't do it.
Can I do only one
Sure, sure.
more question? Usually you have like 4 atoms in a bead, right? So I can't call a coarse grain approach when I have like a united atom that I have like CH2, CH3, something like really small. No, like Trape that you have like the.
So the most famous such model is the Gromos model, and if the developer of Gromos were here and you call that coarse grain, I think you'll get shot. But everything is approximation. We're just having this approximation on top of approximations already.
Like
This
bigger, yeah.
so if you call that coarse grain, I'll be with you. It's an approximation. I mean, you're just collecting 2 atoms in a single particle, so that's good. There's finer coarse grains than Martini that usually you go around 2 to 1. You don't get so much performance, of course, because you have more particles, but those things are possible. Yeah.
Well, there is one online question. I will read as it is written. So, did I get it right that you normally have neutral bits or +1 for the charges, and it's not usually with partial charge?
Yep.
And there is a second part of the question. If partial charges are used, how are they distributed in one bit, and how are they implemented?
Very good. So it comes a bit in the continuation of the discussion we just had. So yes, typically you're going to have only the +1, +2, -1, -2, and apart from that, it's going to be a desert of charge. It's not that these things are not screened, because implicitly we already weaken the electrostatics to account for the effect of the water as a dielectric. Okay, so in Martini, the charge is already 15 times weaker than atomistic, because we are assuming that the water is doing its job. It is not, because water does not have explicit charges, so it cannot explicitly screen. So we are implicitly screening. Okay, that also makes the problem of long-range electrostatics a bit easier, because since our Coulomb interaction is 15 times weaker, cutting it off at 1 point something nanometers is not such a serious deal as if it were not that. Okay, so this is about the charges in the deserts of charge. Now, about the partial charges, this was something that it was always possible, right? You can always do. You can just do the model, you say, okay, you're going to have +0.4, and someone gets -0.4 somewhere else, or you just distribute it in a way that your system is neutral. You can always do it. The problem has always been to be sure that the parameterization, that you know whether the behavior of your molecule is being realistic. Right now with Martini 3, there are some specific particle types that you're going to use if you have a partial charge. These are going to give it a bit more of a polar character, if I'm not mistaken, and these should be used whenever a group of atoms are going to have a total charge. So the group of atoms corresponding that is going to be mapped to the bead has a total charge probably above 0.3, 0.4. Of course, you do still have to find a way of putting the compensating charge somewhere else. And sometimes that's not clear. I've worked with systems where there's such localization of plus charge, but then there's no compensating minus charge elsewhere, and then you risk creating a very strong dipole that doesn't really exist. So it's a bit trial and error for the moment, but if you read the Martini 3 paper, there are tools for you to do that. At least there are particles types for you to use.
Okay, maybe the last question before the break, also online. And if you add fake bonds between the non-bonding particles, does it change your interaction?
Yeah, well, by definition, yeah, you're changing the interaction. Because, but so the question here is how fake is it? How fake it is? The example I showed, we were talking about particles that were in the adjacent rings, and those rings have had a very limited freedom. So I knew that those particles would never really get further than a certain distance. I knew because I had simulated atomistically, and I'm assuming that what I did atomistically kind of represents the range of motion of those rings. So that's fine. Now, let's say you have a molecule that can do this. Open, be more stretchable. Where is the camera? Is it here? Yes. So if you have a molecule that can be more stretched and okay, if you're going to put a bond between these two things, it's going to be hard to represent the full extent of the freedom of the molecule, right? So that's, yeah, that is going to be fake. Then you're going to be missing out on realistic behavior. So that's when you have to be careful about the fake bonds. In reality, the bond that you place there also has a consequence, because in Gromax, which is the software we use, when you place a bond, Gromax automatically excludes those two particles from non-bond interactions. So the repulsion that you're feeling is basically canceled out, because now you have a bond and you're putting them at the distance that you want. So often, instead of putting a bond, it's easier to just exclude them from interacting, and the molecule will probably behave okay. There's even more advanced. So if you don't want to completely destroy this possibility of molecule opening, you can use a sort of a breakable bond. And the trick, the neat trick that you can just use a Lennard-Jones potential. It's a bit like a Morse potential between the particles. And essentially they will like to be like this, but if they go away, because the Lennard-Jones gets flat with distance, they will be able to go away. It's not an infinitely rising oscillator, so we can just break. So these are also possibilities. Right.
Maybe let's do the break.
Yeah, 5 minutes break. Perfect.
The movie is also más compilado.
One of the examples is but if you lose Coarse, but first no, basically, you have yeah, so there is a question. It's used in a lot of descriptions of systems. Right. But mostly if you're looking but essentially, measuring factors or even make your strict. Exactly what I mean. You want multiple pieces of work. No, what's going to happen is you can do whatever you're interested in. If you're talking, let's say, multiple wonders, But sometimes it's useful to say, I can do that. Sometimes I would see, oh, these specific kinds of liquids really interact or not. So I can do an RDF between specific kinds of liquids. There's if you look at this as a system, there's much more non-gross interaction because there's a really smaller. That's one of the mechanisms. You get these possible molecules. There's many more. And then you and it's something that is very used to for a lot of mechanics, right? But even just to say something like, oh, these two guys say two liters, I can say, and now I modify this one with this, and I redo that. And see whether they are enriched or depleted as first neighbors and second neighbors. So they like to be more now first neighbors or longer, so they can preferences and such. And it's very used. It's very used in. It's one of the few things, one of the new analogies that is very important. But the thing is, it's used for different things. It's used for many different things. I mean, I guess this is a bit like the electrophoresis gel and the OMB. Like, you can use a gel for everything, and it depends on what you're doing. And but essentially, it's really the neighboring, like the over distance. So since I don't do so much of the structural characterization, I end up using RDFs mostly for analysis of the. Say, okay, these are like flavors, rich ingredients. Then if you work with membranes, there's also specific cases in membranes you don't want to get a pretty radius, you want to do it just in the plane. Usually you do it low. So if you do like about thinking, oh, if I have the liquid versus type of liquid I will do all 12. But sometimes I might be interested in a specific one, or sometimes I can just relative to protein and just have a single protein. So that's okay, that's my reference, and then everything that's good. So it really depends on the analysis you do. It's actually really good because if you have any background in MD, you'll realize that there are some analyses that are recurrent, RDFs, one of them, stuff like RMSDs, structure and stuff. But from then on, pretty much independent. It depends on your problem. I work a lot with a package called ME analysis, which is really for developing analysis. And I'm always coding my own tools. And if all goes right, it's definitely going to be used. Not really going to directly, but as a script that you send the analysis and then you and it's something very simple. So we're counting contacts. So it's not RDFs, but we're going to we have a protein, we have a lipid. How often does the lipid contact and if all goes well, then we can see nice movements of the little lipids going there and in the protein.
It's all about big stuff.
Honestly, at the course scale, it's quite small. There's people doing way bigger stuff than I'm doing, but there's also it doesn't have to go big or long. In a single simulation, sometimes the power comes from being able to do like 100 different experiments or in the example. I'm going to give you some examples. There's big examples, there's short examples. From the So yeah. So I'm not going to give a solution for your problem because your problem is no. It's one of the problems of the approach, which is it's hard to have an agnostic system that looks at your course when it does the atomistic like that. You really have to give it a lot of information to make it work. Especially because stuff like chirality when you are doing course going. So if you want to, there's very little way of knowing what chirality you have unless course system. Imagine, I'm going to talk about this later, but what you do is a couple of atoms that belong to a part or a beat. And you just place them randomly where they're partners because there's no way to know where they should. This is incorrect. Your chirality might be that's actually the reason. Some force fields, they enforce chirality. Especially the United Atom models. Because they like hydrogen. They don't have all the force fields for a to have the specific chirality. So they have to force chirality. And those they work even better because they already have all the rules. But when you have something like charm that has all the atoms there, if you're not careful, then you. So, and those kind of details are also the technical aspect. The concept is simple. The technical aspect is very. One of the systems that we back not very easy to work with. That's probably the problem you're facing is that it's hard to work with. And the concept is easy. The problem is not very friendly. All right, everyone, let's continue before I give any more spoilers. People already were asking about the next part. So, about multiscale. So, what I'm going to talk about here is how we can combine different resolutions. And this seems pretty appealing, right? You could have the speed up of coarse grain, but in those parts where you actually need detail, you could do it, let's say, atomistic or even quantum. So, this would be great. I'll give a spoiler alert right now. These models are really not working right now. There's not huge advantages in using them. Often you pay a lot of price just to prepare these systems. Everything becomes extremely complex. And the softwares are also not optimized to handle this kind of thing. So because of that, the software runs slower and kind of harms what you want to do, which is actually to have fast systems. So with that out of the way, let's see what the kind of systems you have. There's this address scheme. So this was proposed some 10 years ago, and I did some work with it. It's actually pretty cool. The idea is that you'd have, let's say, a coarse grain region of your system and an atomistic region of your system. And in between, you'd have to have some sort of a boundary where molecules could kind of be transformed from one resolution to the other. So the interactions in this intermediate region would depend, okay, if it's closer to the coarse grain region, it's going to interact more coarse grain. If it's more to the atomic, it's going to interact more atomic. Intuitively, that's the reasoning. There's some problems. So the software, the GROMACS, the software we use to simulate, it's quite fast. So we want to stick with it. But the implementation of address and GROMACS, for instance, when the molecules went to the coarse grain side, they weren't forgotten in terms of atomistic. So you still had to carry all the atomistic atoms. So you didn't get much speed up from there. And also you have a problem, which is coarse grain waters are one particle for waters. So if you have waters, atomistic ones going into coarse grain, how do you keep them together so that they disappear together as four and come back together as four? One solution was to actually use this kind of fake water where the waters are kind of tied together by these bonds. They do have more freedom. They're not always tetrahedron like that. They can distort a bit. It was deemed acceptable, but already shows that you're going to have some issues, right? So you have to start changing the water properties and such. And then it was only available in some software. So already, if you want to use this, you're going to have to go use non-optimized software, which means that very likely whatever speed up that the model theoretical will give you, it's already slower because you cannot use now the latest software and GPUs, and so it's slower anyway. Temperature coupling is also limited. It's not they cannot use all the temperature couplings. The molecules coming back, and the original methods say, okay, if you're an atomistic molecule that went to coarse grain, now you come back, it should be a random structure that gets inserted there. But no, this implementation keeps the atomistic atoms and bonds even when they are in the coarse grain side. So again, not so fast. And this is actually a main issue, that interface region creates density imbalances. And you can imagine this, that no one assures us that the chemical potential of a particle in the atomistic region is the same as in the coarse grain region. And if they are different, means that those particles would like to accumulate in one of those. So you want to have a homogeneous water phase, but then you have some waters that like to go more to the coarse grain side or to the atomistic side, and it's hell. So then to fix that, you have to have kind of faking potentials that in those transition areas push the waters away from the atomistic region so that it kind of compensates for that. It's dirty. Also, you must use some specific potentials, and that means that probably your software also gets slower because of that. And in practice, you don't have any speed up. So, okay, we're not very hopeful about this. But maybe in the future, someone develops an optimized software for this. This one, I always liked this one better than the one before. So in this one, you essentially put your atomistic model, let's say protein here with all its detail, living directly with, let's say, coarse grain lipids and water. So the trick here now is that you have to teach the models how to cross interact. And it's not terrible. So the idea would be like you'd have your atomistic representation, and you would overlay on top of your atomistic representation a coarse grain one. So you can do many softwares. We'd say we create virtual atoms that are tied to the center of mass of bunches of other atoms. And how it would work is, so the atomistic with atomistic, let's say this part of the molecule atomistic with this one, they would interact normally with atomistic potentials. So that part is fine. So the coarse grain with coarse grain interacts coarse grain. That's fine. These centers of mass here that I've placed, they don't interact with one another. So this part of the molecule and this part of the molecule, they're going to interact atomistically, but not through this coarse grain center of mass. That also makes sense. Now, the interesting part is, then these centers of mass are going to be the ones interacting with these coarse grain particles. Okay, so that's how you interact with the Lennard-Jones part. But then, like this. And then the partial charges interact directly, the ones in the atoms with the ones in the coarse grain particles. So this is a way of kind of compatibilizing these two models. And honestly, it seems pretty promising. The big problem here, again, coarse grain is a landscape of almost no charge. And then you have all this, now you have all these small partial charges floating around in that charged desert. So everything gets extremely strong in terms of atomistic charge interactions, because honestly, these things usually, if you're in that atomistic world, these things live surrounded by other partial charges that constantly screen it and such. And suddenly, in the coarse grain system, this is not the case. So what you have is something like this. If you're looking at NaCl, or even just something like the salt bridge in the protein. So in black here is the energy profile. So this black line here is the energy profile as a function of distance of how these two residues should interact. Of course, there's going to be a minimum somewhere there because these are opposite charges, so they would like to be together. The thing is, you don't even see this because if you do this in coarse grain in a model like this, because there's zero other screening, these things are going to be sticking, but like with stupidly high energies. So far, this is the main and the big problem of this kind of model. All right. So yeah. But now, just to end on a better note, the final part of this multiscale. So there's another kind of multiscale, which is maybe less visually exciting because things are not going to be living together as different resolutions, but is the sequential multiscale, where you have something that is coarse-grained, and then you change it to atomistic, and then you can continue your simulations. It makes sense, for instance, if you use coarse-grained to find some interesting states of your system, let's say a pore in the membrane, or a binding between two proteins, or something like this, stuff that takes a long time to reach, that therefore you need coarse-grained. But now you need to know how this would actually behave, of course, atomistically, just as a control to see if coarse-grained is doing it right, but also maybe because now you need some more details in stuff like secondary structure changes, chirality, etc. And the idea is that you have a system like this. Oh, sorry. In the normal part of coarse-grained, you can go from atomistic to coarse-grained. That is very direct, right? You just have to have those mapping rules to say, okay, this bead goes on top of those atoms, and boom. But how about the opposite? How about starting from here and going there? There's more models now emerging, but the one that I've used the most and is still quite used, and actually there's quite some tutorials about this in the Martini website. It's called the backward. And the idea of backward is the following. So you have your molecule. I mean, and this can be for all the molecules in the system. It doesn't have to be one by one. And you have to have some information that explains the mapping of this model of the atoms to the molecule. Oh, sorry, of the atoms to the coarse-grained molecule. And then what you do is, the program does for you, but you go to this very last particle, for instance, and you see which atoms belong to this particle, which atoms are mapped to this particle. Oh, okay, so this is 1, 2, 3, 4. So they will be semi-randomly placed around the center of mass of the coarse-grained particle. Same thing for each of these particles. Okay? This is semi-random. There's some information there because we also have, if you want to do back mapping, you need to have the atomistic topology. And the atomistic topology, there is information like this atom is bound to this atom, which is bound to this atom. And if this atom belongs to this particle and this atom belongs to this particle, then I don't need to randomly place these atoms because I know that those two that are connected should be closer to one another with respect to the center of mass of the corresponding particles, right? So if these atoms are all going to be around here, but this one is connecting with the next one, so I'm going to place this one already closer to the next one. Just some clever stuff that the program does that helps it getting closer. But stuff like hydrogens, they still get kind of randomly placed. You see that, yeah, there's some detail here, but this is not a real molecule, right? Then what's done is a series of energy minimizations and equilibrations while restraining overall the distance between each group of atoms and the corresponding center of the coarse-grained bead, right? So you're gonna now release the system or equilibrate it, but still retaining some distance to the coarse-grained representation. It looks something like this. So it's going to be a movie. The beginning is the coolest part because the hydrogens are going to just boom, something like this. So this is energy minimization, and so it's trying to find the comfortable part. There's an interesting part here is that this is a lipid, and in lipids, most of the times this oxygen is pointing out, and this one too. And this one is not yet very comfortable. At some point, it will find its outward pointing position. So it's there. There we go. Right. So it works pretty well. And then after that minimization, you can actually do a very gentle equilibration. That's what's happening here. As you slowly remove the restraints from the center of mass of the coarse-grained, and there you go. You have your atomistic model. So drawbacks. It's not really straightforward. You do need to have that mapping file that explains how to get your beads from your atoms and vice versa. But that's probably not enough. you have to give it also the atomistic topology information, and sometimes you don't have it. I have that problem right now. I made a molecule, coarse-grained molecule directly from a molecular model, not from atomistic simulations. Now I want to do back map, but I don't have an atomistic ITP for it, and I don't have an atomistic topology for it. So that's going to be very annoying. And you have a lot of placement constraints that has to do with the chirality and stuff that you might need to preserve. This is an image from the paper where this is described. So it can get complex, and also technically it's difficult to implement. This is sadly a downside, right? But I've never not been able to do a system. So systems don't. I don't think there's impossible systems. They're just maybe annoying and hard. Okay, so any questions about the multi-scale part? Because now we're going to the movies part, the application. So questions? Quanto, if there's any questions online, then you can let me know, okay? Thanks. So application. So this is the cool part. So we explain how to get there, what's good with the model, what's bad with the model, but so what can we do with it? And the very first successes of this kind of models were with lipids. Perhaps also because they work well if you just have a very basic representation of hydrophobicity and hydrophilicity. So you can make membranes, and even more than membranes. Now you can even start looking at the phases of a membrane. So if you have, let's say, a saturated lipid, at low temperatures, it will get kind of a crystalline organization, and you can see that, and it gets reproduced. You can also do vesicles. This is just several vesicles cut in half just to show that you get several sizes. So that's all doable. One thing that I like a lot, because I work with this a lot, is the coexistence of bilinear phases. And this has a very tight connection with biology. So if you have a mixture of lipids, depending on the mixture, they can do laterally segregated domains. And you can see that in microscopy if you have specific dyes for each of those kinds of domains. That usually happens if you have mixture between saturated and unsaturated lipids and also cholesterol in there. And it might have biological consequences. I don't know if you've heard of the raft hypothesis, but the idea is that you'll have domains with different physical-chemical characteristics, because ones will be enriched in saturated lipids, the other ones in unsaturated. And that might provide basis of attachment for different kinds of proteins. And so basically you do sort of compartmentalization based on the types of the domains. And these kind of things are all super important: signaling and efficiency of biochemical reactions. So it's still a hypothesis. There's plenty of evidence for. There's also some evidence against. We try our best to also try to address something in simulations, and we're going to see something. So this is just a basic example of this. What you're seeing here is a membrane seen from the top. There's three types of lipids. There's DPPC, which is a lipid that only has saturated tails, so more ordered. D-linoleal PC, so basically this is a polyunsaturated tail lipid, and cholesterol. And what I'm showing here is just the lipids of the top leaflet, and only the beads, the first tail beads of each lipid, right? So that's why there's only, you can see they go in pairs, okay, like this. Each of them represents the top of the tails. The cholesterol only has one particle. So they're randomly distributed, but within something like 7 microseconds, I can see that the saturated and the cholesterol, they go to make their own little thing, and then you get a phase that's enriched with the remaining lipids. So this is a cool parallel to what we can see in experiments in those vesicles with artificially produced lipids. Great. Now we can try and go and be more daring, and this is what we did in 2014. So back then, this was a record of complexity of this kind of systems. We had this is 80 by 80 nanometers, so this is several million particles. I don't remember now exactly. And remember, if you convert this to atomistic, it's at least times 10. We had 63 different lipid species, and we're trying to represent what would be a typical plasma membrane. So what we're trying to do here is trying to see whether that raft hypothesis, that domain separation, happens in vivo or not. So if I have a realistic membrane, does it separate into domains or what? The answer actually was not super clear, even though we did simulate for several microseconds. So we do see the association of a lot of saturated lipids and cholesterol together, but it's much less clean cut as we saw if we have a much simpler system. So the jury is still out, but I really liked working in this project, and it was good to be able to give input there. So this is another thing. So now proteins and actually protein functionality. This is a protein that it has many functions, but in bacteria you can think of it as a pressure release valve. Let's say your bacterium, suddenly someone drops distilled water on you, you start taking in water because of osmosis, and you might just burst because of that. So it might just be better to just have some pores in your membrane that open and let some osmolytes leak out rather than exploding, right? So, and this protein does that. Incidentally, you have a homolog in your touch. Your touch is also mediated by this, as you can see, because of pressure and stuff. Anyway, it's a very simple thing. And the system is, we have this protein in the membrane, and we're going to pretend that there is tension, like there is osmotic tension, not by really inflating the membrane. It could be done. This system here was done like that, like water was pumped into a vesicle till it's really exploded. But in this case, it's much simpler to actually just stretch the membrane, because that's the consequence of having pressure inside a cell, like the membrane is going to be stretched. So it gets stretched, it gets thinner. And what was seen is that this protein can actually respond to functionally respond to the stretching. So it's a channel that's closed and becomes open and then can close again. So this is quite cool. And you might ask, well, but you just said that Martini cannot do protein structure, and you're seeing the structure changing and coming back. And in this case, we still had to restrain the structure, but we only had to restrain the individual helices. So each helix was kept as a helix, but all the other helix-helix interactions were mediated by the normal non-bonded Martini. So they were free to unfold and refold in that sense. So the tertiary structure was not restrained. And to be honest, this was, I'd say it's a lucky break. It's a system that responds very well, it behaves very well in this sense. I'm sure there's a lot of other systems that the tertiary structure will not be accurately represented. But there's a movie of this in action. So this is the existing system. And what's going to happen here, so you're seeing the membrane from the top or from the side. And right now there's a blockage here. There's some water on the side of the protein, but there's a blockage here, so the water cannot pass through the protein. And what's going to happen is that we're going to put tension. Tension is this green line, so we're going to increase the tension and leave it open, and then at some point release the tension. And then you can see here is the radius of the whatever pore formed versus how much water is going through, and you get something like this. It's very quickly spreads out, the pore opens, and you can see then that the water's coming through. And after a couple of microseconds, you release the tension. You see that there is a response. It's not immediate, so it takes a couple of microseconds for the structural reorganization to occur. At some point, this hydrophobic lock gets established, and there it is, and it goes back to being closed. So this is super cool. You can actually see protein function in motion, right? Next, okay, lipid protein. This I really like this one. I'm still working in this project. This one is not necessarily big in terms of system size, but so what we had here was, so we had colleagues in the lab in Germany, and they were able to hijack the synthesis of ceramides in our cells and put them in the mitochondria. I mean, even for me, I'm a biochemist, I'm like, yeah, what's so important about that? But it turns out that when you place ceramides in the mitochondria, you trigger apoptosis, so the cell death or spontaneous deliberate cell death, and that might be very important because there's a lot of things related to that, cancer and stuff. It's okay. And so what they did, they wanted to know, okay, what do the ceramides? Ceramides are, as you can imagine, they are like short, not so polar lipids. So what do they do in the mitochondria? And they used some click chemistry to figure out that they would preferentially bind to a certain type of proteins. and which is this protein here. But they didn't know much about that. They knew they were a binding partner. That's it. But is there a binding site? How does the binding happen? No idea. So this protein is a channel. But the fact that it's a channel right now is not going to be so important because we are looking at the mitochondrial membrane, the outer mitochondrial membrane. So this is all membrane. I'm just hiding all the other lipids. And the ceramides, because they are lipids, they are actually in the membrane. So the fact that stuff can go through the protein right now is not going to be so important. And what I'm going to show you here is that, okay, we took the protein, it's called feedback, and we put some ceramides there, and I'm going to show you a particular one. So now from the sides, and we have the ceramide. At some point, ceramide goes there and finds the binding site. It's very obvious, right? So this is part of the practical of this afternoon. Actually, this is most of the practical this afternoon, right? And this is there for a while. Pretty cool. And then it leaves. In this case, it even left to the opposite side. So we could even think that maybe these things can have a flipase activity, catalyzing the flipping. Although these lipids, they already flip quite a lot on their own, so maybe not so important. Anyway, this was super cool because we could say, okay, there's a binding site and maybe flipase activity. And this would be very cool because then we in the simulation could just mutate this. This is the glutamate, and it's already suspicious. Why would the glutamate be facing the membrane, right? But we could mutate this to a glutamine, and then this stops happening. And then the people did that in the lab, and then stops apoptosis, and then this back and forth. It's very good because then it's not just us justifying what people did in the lab, then the people in the lab go and justify what we did in the computer, and everyone's very happy and feeling very good about themselves. So that was very nice. But the power of the coarse grain here is, I'll just show you like 2 microseconds of 125 of this simulation alone. I did like 5 replicas of this system. So in total, we had something like 1.5 milliseconds of simulation in the total of several replicas and 700 binding and binding. We had hundreds of binding and binding events. And then when you have those numbers, those kinds of statistics, you can start computing stuff like residence times, affinity constants based on explicit times that it's on and off. So you can estimate K on and K off and get affinity from there. We need to do this because there's 2 variants of this protein. And I wanted to know, does it prefer one or the other? Does it stay bound longer to one versus the other? And then you need statistics to talk about that. And coarse grain allows you to go into the millisecond without a lot of effort. So very good. Next. Oh, this is also very cool. This is a project that we still have ongoing. This is an earlier simulation. So we had some colleagues that have the structure of this this enzyme. It's an enzyme that it's a bacterial enzyme, and it gets electrons into the respiratory chain. So if you're not familiar with the respiratory chain, essentially at some point an electron donor is going to come from the cytoplasm, and somehow the electron has to end up in these guys here, which are quinones that will be reduced to phenols, and they will continue on to power the bacterium respiration. But essentially, we want to see, okay, there's no electrons in coarse grain. Okay, we're not going to be seeing electron transfer. But I'm already very curious to know how this protein, which is known to be monotopic and not always associated with the membrane, so it can be out and on the membrane and out of the membrane, how this protein could be interacting with this quinone, especially when the binding site is kind of inside, and the quinone is a lipid. So can it be pulled out? And actually, it's very cool because we do see that over time, and I think I'll speed up a little bit. Over time, there is one quinone. Actually, you can see it's starting to climb towards the binding site. Towards the end. There we have it. This one is pulled pretty much all the way to the binding site, and mind you, this is a protrusion out of the membrane that the quinones never go on their own. We can see the other ones; none of them has taken out spontaneously like that. But this is very cool. We can see the catalysis of this reagent sequestering into the binding site. Right now, what stuff that we want to do after this is, okay, after it's reduced, now it's a quinol, what happens? Maybe the affinity is lowered for the binding site, and the thing just gets shot out because it's no longer has affinity for it and has a lot of affinity for the membrane. work in progress. So it's exciting times. There's a lot of other stuff. So these examples are still from Martini 2. All these things right now exist already for Martini 3. And the things that exist for Martini 3, they are super exciting because this is a brand new. The model came out last year, and now little by little, a lot of these parallel models are coming out because we have the generic Martini 3, and now we have, okay, now from 3 or 4 months ago, we have the sugars and stuff like that. So there's DNA. So DNA will probably take a bit longer, but it's already exists for Martini 2. Just as with the proteins, in some cases you will need, you might need this elastic networks to keep structures. But honestly, in many cases it works pretty well. And there's a host of other kinds of molecules. So this is it's ongoing, and based on what we already had for Martini 2, I think we're going to have a lot of representativity that's going to be very useful. So earlier this year, we had participated in a review of the 10 years or 20 years of Martini, 10 years of Martini 2, something like this. And this is a part of the slide about the complexity of the system that So you have this very complex system that we did of the lipids that I showed earlier, but then we've moved on, and now we're doing those complex lipid mixtures, but now with proteins, just to see how often certain lipids interact with proteins, what's the lipid fingerprint around the protein, also mixes of different, in this case, different oils. Doesn't have to be all membrane. This is just different oil, organic solvents, water coexistence, and extraction. So things like fish oil extraction of some compounds, pretty cool, and also a lot of systems. And then if you go to polymers, now you have this really cool mixes of many different polymers. Also an area where Martini is advancing a lot. So that's very cool. Actually, part of this figure was the record, like the number of different molecules, different types of molecules in the system. So you start with simple models that has like water plus 2 or 3 components. Then you go to 4, 5, 6, and then boom, it's 60 something. And now I think the record now is 64. And then you can even go into the mesoscale. So this is already part of the efforts to simulate the whole cell at the coarse grain level. It's exciting. I hope it happens in the future. It's not just coarse grain. There's a lot of implicit other models. There's no water, but there is explicit lipids. There you have a whole mitochondrion with explicit lipids. So this is a pretty cool work. And that's it. So thanks for your attention. Questions?
In hybrid simulation, like where you have, for example, you said the protein at atomistic level and lipids at coarse grain. In this way, we reduce the amount of atoms, for example, but what would be the time step of the simulation? Like, can we go from, because at atomistic level, we would be at 2 femtoseconds, but can you go to 20?
Yeah, exactly. Yeah. Typically,
how can you regain the atomistic interaction at a larger time scale of the?
No, atomistically, there's no. You meant the hybrid. The hybrid. Yes, that's problem. In principle, you could do something like dual time steps, where the atomistic atoms, they would have their forces updated every 2 femtoseconds, but you only do the coarse grain ones every 20 or so. The problem is that the engines nowadays, they don't do that because they're not programmed for that. So no engine right now is optimized to do that properly, or not that I know. So you don't gain that much there. To be honest as well, like the coarse grains part is going to be 1/10 or so of the entire system. So yeah, you're going to speed up 1/10 of the system. You're going to speed up by 10 times, but only 1/10 of the system. So you're not going to gain that much. But yeah, it's a problem. You can push atomistic up to 5 femtoseconds if you get rid of the fastest degrees of freedom. Again, it's the same problem of the stiff harmonics. So use constraints as much as possible. And if you use GROMACS, up till recently, it was possible, not very easy, but possible to use, especially if you're working with proteins, to use virtual sites to represent ring moiety. So the problem is always the shortest, strongest bonds. And in this case, we become the CH bonds in the phenyl rings, right? They are short bonds and they are very high frequency. And if you just use virtual sites as a strategy that you can, basically they just become, essentially you're describing that as a rigid body. And you don't have to worry with the time step to recreate this very low amplitude, high frequency vibration of the CH bond. Yeah, that would be a trick. But that goes for everything. It doesn't have to be in a hybrid model. Yeah.
So the first when you simulated 20 femtoseconds more or less.
Yeah, so that's the traditional one with Martini, and this is for Martini. Other models might be able to go further. We try to put out models that are at least stable at 20 femtoseconds. Usually we try to make them stable at 30 so that we can be confident at 20. It's very cool. It's a part I like, to just push them to break and then try to figure out what's breaking and try to fix. So yeah. Also, if you start pushing the time step, you might start losing some representativity if the model was parameterized for one time step. So.
There is a question online. So, how do you define the boundary between the all atom and the Coarse ring?
How
do you define the boundary region?
In
all
that,
atom and the Coarse ring.
yes. I imagine that's about that address scheme where you had this this in between region. One of the rules is that you don't want to have any atom that is in the completely atomistic region interacting with any particle that's completely in the coarse grain region. So that has to be at least larger, thicker than your interaction cutoffs. So that's the first rule. The second rule is that, not rule, but it's probably needed, is if you want to see interesting atomistic stuff there, you probably need to choose an area that includes the stuff that you want to see. As I said, there's not a lot of speed up to be gained there, but the smaller the atomistic area is, of course, the biggest the speed up you're going to have. So that's those in that system. It's those are the main rules, and you don't want to make it thicker than it needs to be because it's an expensive part of the system.
About the back mapping, you said like it is a little difficult to perform the back mapping. So like I was just wondering like what do we do so that we can do the back mapping very efficiently so that we don't end up in a very either we will not get any results or we.
I would recommend, so there's a lot of resources in the Martini web page, including several tutorials of back mapping using this software which is called Backward. There is also other alternatives. So this method, the method that was used to do this kind of simulation, can also be used for back mapping. Of course, it's going to be a totally different approach, and there's others coming up. So you might decide to just go a different way. If you do stick for this backward, the problem has not been developed progressed in a while. I mean, it still works, but I mean, there's some bugs or some errors that it's not very obvious what you're doing wrong, and that's where the frustration can come in. I guess doing first the tutorials should help because those should work.
About the tutorials, so I've tried the tutorial files, like it works perfectly fine as the way it was given in the tutorial. But when we try to use it for our own system, like it doesn't work in the same way. Yeah. So like I really don't know like what other parameters that we need to really consider for to overcome this kind of situations.
I guess the answer here is like, okay, what does it mean it doesn't work? Where does it crash? And the problem is often the feedback you get from this kind of programs is just Python error somewhere.
Yeah, that's sort of thing.
Yeah, and that's not, and I know that's not helpful. I don't have an easy solution for you. Since I also work a lot with Python, sometimes I just go after those small bugs and I realize, oh, okay, this is what's happening. And it just, but if you're not fluent in Python, you don't have that flexibility. So you might be out of many options. So it might be interesting to try and exploring other solutions like the TS2CG, which is the program. There's also tutorials for that. So maybe that could be a good option. Of course, there's the the forum, you could ask in the forum, but I'm not sure you're going to get very specific help. I mean, because those problems tend to be very specific, and it's very hard to get that kind of very specific help like that. But I mean, good luck. I mean, I already said that it could be problematic precisely because I've been through that. I know it's
what kind of backmapping methods that you are trying to?
I use the backwards, the one backwards. Yeah.
Okay, the last one maybe before
I have another question about the backmapping. Is there always a unique way to do it, or could it be some ambiguity?
No, definitely there's ambiguity, right? And that's a big part of the problem. There are some Coarse models that are finer than Martini, and they always retain the option to very cleanly specify all the positions of the atoms. So especially if you have mappings that are around 2 to 1, it's almost always sure where the atoms are going to be, especially because you have one bead, the other bead, if they are connected, if the atoms are connected, I know that this one is being bound to this one, that's to that one, and that pretty much solves a lot of the problems. Here, there's going to be ambiguity. So there's the program still uses this kind of hints to pre-place some atoms closer to where they should be. The rest is placed semi-randomly. And then we hope that by doing this energy minimization, while restraining the atoms overall to the place where the bead is, that the final structure is representative of what it should be. So that's exactly the thing. Also, because of that, you have to have the care to preserve the chiralities, for instance, because if you do not place the chiral centers in the correct configuration, if they are randomly placed, you might end up with inverted centers, and that's not good.
Okay, thank you very much, Manuel. Finally, we because
The ones that
Ojalá, ¿no?
You mentioned the difficulty of proper description of I was wondering how
The debugging part,
Sorry.
the debugging part, the more snow. Yeah, I wanna cry. And you solve one.